All right. This is going to be practice exam 6 version A. Hopefully this won't be as bad as the first one. I don't think it would. So let's start with 6.1. But before doing it, we can see that for problems 6.1 to 6.3 refer to the two variable function. I'm going to just write it right here. It's going to say z equals your f of x, y, which equals the square roots of 3x squared y plus 8xy squared, right? And it says at the points at PO of 2, -1, 2. Okay, so this is given to us. And we have to use this for 6.1 through 6.3. All right, so let's do 6.1. It says write the general expression for the gradient vector of the delta or whatever that is of f xy. So to do that, we know that the gradient vector is actually equal to your f of xi plus your f of yj. Reason why I know that is because I think it says that in the memorization page. So I recommend you print that out and just keep it for yourself so you can refer to that. Or just to make it easy, because I think he wants it in whatever these things are called. I forgot what they're called. F of x, comma, f of y. All right, so that's the equation for a gradient vector. We have to find an f of x and f of y. And it's pretty simple. Remember how we found our f of x and f of y for our last exam? It's going to be the same process for this one. All right, so we're going to find the partial derivative of x with respect to y. This is going to be the derivative of x of the equation of our thing that was given, which is this equation right here. I'm going to underline it in red right here. So actually, I'm going to make this also red too, so it can be a little different and we can see it better. So it's going to be 3x squared y plus 8xy squared. And when we find the derivative of this, we know that before doing anything, we have to make this to the power of 1/2. That's equivalent to a square root. And just by algebra, calculus, whatever it is, we get, I'm sorry if I'm not explaining how to get this. It's just time constraints and stuff like that. It's going to be 1/2 to the square root of this value right here. So nothing changes. It's a chain rule process. So you're going to take the parentheses of your square root first. So it'll be 1/2 to the square root of 3x squared y plus 8xy squared. So that's it. That's the first part. And now we got to find the derivative within the square root, because that's how the chain rule works. And so we're taking it with respect to x, or d of dx. So we're going to have right here, we're going to have 6xy plus 8y squared. How did I get this? Is because 3x squared, the derivative of 3x squared is 6xy plus 8, and the derivative of x is just 1, so 8y squared. So that's what you get for the first part. And from that, we get that the derivative of with the partial derivative of f of x, remember this is also equivalent to your f of x, remember that, is equal to your 6xy plus 8y squared over your square root, or 2 to the square root of 3x squared y plus 8xy squared. You could simplify this. You could take a 3 out and this, take a 2 out. Yeah, and then this will just be 3xy plus 4y squared, and then you can take out the 2 in the denominator, but he just left it in there in the question. So yeah, so that's your f of x first. We already saw it for our f of x now. Now we got to solve for f of y. And it's just going to be the same process. I'm going to clear the screen, so hopefully you write this down. I'm going to just do a brief recap of what we did. Like we said, our gradient vector, you have to find your f of x and your f of y. This is in Cartesian notation. This is just in whatever the notation is called. And so, yeah, to find your f of x, you're just finding the derivative of your d of x. And I think that's what we did for the first one. Yeah, your f of x is just your partial derivative of your f with respect to x, which is just taking the derivative of whatever equation you're trying to find, which is this right here. So yeah, we took the derivative and then we got 1 over 2 times that square root right there. And then due to chain rule, we got to take the derivative of this, and this will be 6xy plus 8y squared. So in n, we got this for f of x, 6xy plus 8y squared, 2 over 2 to the square root of 3xy plus 8xy squared. Alrighty, now let us do the partial derivative of f with respect to y now. So I'm gonna clear this drawing. Hopefully y'all wrote everything down. Now let's try to find the partial derivative of f with respect to y. But like I said, it's just gonna be f of y, which equals, that's supposed to be is equal, I don't know why that says a z, which equals the d of dy times whatever that equation was. I'm gonna look back to what our original equation was, and it was 3x squared y plus 8xy squared. And taking the derivative of this, like I said, it's the same concept. Remember, you got to take your square root out first and make that, find a derivative of your square root, and that's going to be 1 over 2 times this, whatever's inside the square root, y plus 8xy squared. And then we have to find the derivative of what's inside the square root due to the chain rule. And now we're finding it with respect to y and instead of x. So it's going to be 3x squared, because the derivative of y is this one, plus 16xy, because y squared is just 2y, and 2 times 8 is 16, and 16xy over 1. And now we get that our f of y value is just going to be 3x squared plus 16xy over 2 times this, well, I'm just going to rewrite that. That looks disgusting. All right, so 2. Then, well, my whole thing looks disgusting, and it's just that looks even more disgusting. All right, so yeah, so there you have it. So it's going to be 3x squared plus 16xy over 2 to the square root of 3x squared y plus 8xy squared. I just had a brain fart there. I apologize. Please tell me I'm recording. Yes, I am. Okay, I sort of got if I wasn't. All right, so there you go. That's your f of y. All right, so all we're doing now is just plugging it back into that gradient vector equation. Like we said, the gradient vector equation was just your notation of your f of x comma f of y. So putting that into the equation, going back to that previous slide before I erased it, our answer was 6xy plus 8y squared over 2 to the square root of 3x squared y plus 8xy squared. So that was our f of x. This right here. Let me just undo that right there. Let me just change the color. Remember, this is our f of x that we solved in our previous example, and then this one will be f of y. Hopefully I can get it into that so I don't look stupid. All right. All right, what was I gonna do? All right, so put a comma because you need a comma right there. And then now we're just gonna plug in our f of y value, which we just solved just recently. So it's 3 of x squared plus 16 xy over 2 to the square root of 3x squared y plus 8xy squared. And there you go. There is the general expression for the gradient vector. Like I said, you could simplify this by taking a 2 out. So this would become 3xy plus 4y squared, and just canceling out the 2 in the denominator. But he just left it like that. In my opinion, I would do it. I don't think he will care. But yeah, this is your answer. Let me just circle this all in a blue color and say this is your f, your gradient vector. F of x, y. And there you have it. That's your answer for 6.1. Now, 6.2. Let me just clear this. I'll give y'all like 2 seconds. 1, 2. All right. Hopefully y'all either paused it or like, you know, this is say 1. Hopefully y'all pause it or anything, or yeah, whatever. All right. 6.2. 6.2. Now we have to find the directional derivative du f whatever that, you know, it says du f of xy at point po in the direction of a equals negative 5i minus 12j. All right, So it might look confusing, but it's actually pretty straightforward. We know that our equation for our direction, or whatever it says, du f of x, y. Reason why I know this is, like I said, it's in the memorization sheet that he gave us. So it's going to be, this will be equivalent to your gradient vector, basically. This is basically your gradient vector times your unit vector, u. Okay, so this is your equation. Your gradient vector of f of xy times, this is a multiplication, times your unit vector. And we already know what our gradient vector was. Our gradient vector was what we just had, what we just solved previously. But the only difference now is that find a direction derivative with respect to our p point value and the direction of a. So we know that our p naught was equal to 2, -1, 2, right? But here we only have your x and y values. So you don't really have to give any care about this 2 right here. I really want to say curse words, but I'm sorry. All right, so this is going to be 2, -1. You're just going to pay attention to your 2, your x value, and your 1, which is your negative, and your y, which is your -1 value. All right, you're just paying attention to these 2 values. All you're doing with this is that you're going to plug it back in to that gradient vector equation or general expression that we solved for. So I'm going to just do that right now. So right now I'm going to solve for this right here. And this is going to be 2, and this is going to be -1. So you're just going to plug it into that original equation. So it's going to be 6 times 2 times -1. Okay. Remember where I'm getting this from, right? This is 6xy. 6xy plus y squared, which is -1 squared. Remember, this is the f of x value. All I'm doing is just plugging in the x and y values into the f of x value that we solved for. 2 times the square root of 3 times 2 squared times -1, because this is 3x squared y, plus 8 times 2 times -1 squared. Okay, so this is your f of x value. This is your f of x value, and I'm gonna do the f of y value in a different color so it doesn't look all jumbled up like that. All right, and remember, f of y value is your 3x squared plus 16xy over the 2 times the square root of 3x squared y plus 8xy squared. Remember, just look back into the answer sheet because, you know, it's pretty, I'm only working with one monitor right here, so I apologize. So remember 3x squared, so this is going to be, oops, let me just redraw that. 3x squared is going to be 3 times 2 squared plus 16 times 2 times -1, right? Over 2, and then this is going to be 3 times 2. This is going to be the exact same thing as the one on the left side because nothing is different from the denominators of both your f of x and your f of y values. So this is going to be 2 times -1 squared. All right. Okay. So there you have it. You have your value of your gradient vector. When you put this into the calculator, you should get, this should be -1, -5. You should get this. If you don't, I'm extremely sorry. My condolences. Okay. All right. So yeah. So -1, -5. That's your values that you get for plugging in to your f of x and your f of y value. Okay. So we have that. We're not done. Now we need to find your unit vector. All right. So from that equation, I'm gonna try to keep this in the same page. From that equation, we're given that your a value, or your acceleration, is -5i minus 12j. Okay. And keep in mind, this is a dot product, right? So a dot product is the product of multiplying 2 Cartesian coordinates. So this right here is a Cartesian, well, this is not Cartesian, but this is the other form of the if you want it as Cartesian, it'll just be -1i. Holy moly. All right, so this will be -1i minus 5j. This is the Cartesian coordinate, but you can write it as whatever he wants this. I really don't know what this is called. Here, we're not gonna multiply this value by a, because that's not your unit vector. That's only an acceleration. To get your unit vector, remember that a unit vector is going to be your, whatever your acceleration is, so negative 5I minus 12j over the magnitude of that. So it's going to be, this is how you get your unit vector. Wow, I made that look exactly like a. All right, so this right here is how you solve for your unit vector, u, right? So keep in mind that a and u are two different things. A is just a vector. U is the unit vector. To solve for your directional derivative, like we have here, which is the f of x, y, you have to multiply it with your unit vector, not the a. So if you multiply this with the a, you will get a different value from what is being listed. So right, so when we solve this, we get, so the denominator, so the square root of negative 5 squared, negative 5 squared plus, oh my god, so negative 5 squared, if I can, I swear to, all right, so negative 5 squared plus negative 12 squared, this will give you a value of 13. So your unit vector is negative 5 over 13I minus 12 over 13j. This is what you're going to multiply your negative 1I minus 5j with. You're going to multiply this or do the dot product with this vector, because this right here is your f of your gradient vector of f of xy, or in this case, so this will be 2 and this will be negative 1. And this right here is your unit vector. Okay, so I'm just going to try to make as much space as I can. Like I said, I do apologize if, like, you know, this is not organized, but I'm doing my best here. You know what, forget it. All right, I'm gonna just do a new page just to make it more organized. All right, so like I said, we were given solving by plugging into those values into the gradient vector, we got negative 1, negative 5. And then by finding a unit vector from that given a value, we got negative 5 over 13 I. Oops, sorry. Since we're doing this type of thing, we're not going to do Cartesian coordinates. And negative 12 over 13. Okay. So all you're doing to get your d of u of f, give me a second, of your f of what is it, two values? It was 2, negative 1, right? You're just going to find the dot product of those two things. So negative 1, negative 5 times negative 5 over 13, comma, negative 12 over 13, right? Okay. And I hope you guys know what to do to dot product, but I'll just show here. So this is going to be negative 1 times negative 5 over 13 plus negative 5. Oh my god, my handwriting is so trash. I'm telling you, this is not how my handwriting looks. All right, so this is going to be negative 1 right here. Negative 1 times 5. Negative 1 times 5 over 13, negative 5 over 13, and negative 5 times negative 12 over 13, right? So let me just finish this. So negative 12 over 13. Okay, and this will give you the value of your d of u, so or your directional vector. So this will be your f, 2, negative 1. So by plugging all this into your calculator, all this, you should get 5. So let's see, negative 1 times negative 5 over 13 plus negative 5 times negative 12 over 13. And yeah, it gives you 5. So there you have it. This is the answer for 5.2 or 6.2. I'm sorry. That's how you do it. This is supposed to be a unit vector. I know it looks like a y. I do apologize. U. So there you have it. That's the answer for 5.2. 6.2. Oh my, 6.2. 6.2. 6.2. There you go. All right. I'm gonna give you all 2 seconds. 1, 2. All right, now we're gonna do 6.3. 6.3 is actually, I didn't even need to erase that. I could have kept it. So it's just asking, what is the maximum rate of change of z equals f of x comma y at p naught. So all it's asking is finding your maximum directional value. So your max du of f given the points of 2, -1, right? Or actually, let me just give you the general equation first, because I don't want to like. So the this is the general equation. I'm pretty sure this is in the memorization sheet as well. Maximum times your d of u f of x naught y naught, which was 2 and -1, equals, all you're doing here is just finding your absolute value of your gradient vector from those two numbers that we plugged in, which was the x naught, y naught. So when we're finding the max, I'm gonna rewrite it again, but this time with the values. So du, so now I understand why he's saying this is a repetitive process. So we had our given numbers, which was 2, -1. This is from point P. Remember, point P was 2, 2, -1, and 2. But remember, we just care only about the x and y values because we're not given a z value to solve for. If we were given a z value to solve for, then we would consider this 2 right here. But we're not. We're just, all we care about is the x and y values. All right, so going back, it's going to be equal to the absolute value of the gradient vector with those two numbers that were plugged in. So it's going to be 2, -1, -1. And remember, this is the absolute value. And we already solved this. Remember that our gradient vector from plugging these two in, let me do a different color because I want to make it as clear as possible. So remember, when we plug those two values in, the 2 and -1, we got -5, 1, right? Let me move this a little bit to the right. So this is going to be -5. Wait, let me make sure it was -5, 1. Was it -5, 1? -5. I'm sorry. It was -1, comma -5. I'm not sure what I did in the previous problem, but hopefully I also put -1, -5, but it was -1, -5. And all you're doing is finding the absolute value of that. How do you find the absolute value of this? All you do is just find the square root of -1 squared plus the square root plus -5 squared. That's how you find the absolute value. And from doing this, we know that our max of d u f equals of f of x of 2, -1. This will equal 1 squared plus 25. So 26, the square root of 26. Is this the answer? Yes, it is. So this is the answer for 9.3, 6.3. Yeah, 6.3a. This is 6.3a. Let me say a right here. All right, and b is straight up like straightforward. And what vector direction is the xy plane maximum at the rate of change of p naught? All you're doing here is just plugging in that value of -1, -5. This is where we solved the maximum value. So this is the Cartesian vector that you're answering. So the answer is just this right here. Let me do that in a different color so you know. So the answer is just this right here. You're just plugging in -1, -5 for part B. And this is the answer for part A. So yeah, it's pretty straightforward. It seems pretty threatening at first, but it's not that bad. Not that bad. All right, so I'm gonna give you all 2 seconds. 1, 2. Nice. Let's go to the next one. 6.4, we're almost there. So now in 6.4, we're given 3 variables this time. Now we're given x, y, and z that we need to care about. If you're thinking that this might be a little more difficult, it's actually not. It's actually pretty straightforward. Well, because of the problem that he gives us. I'm not sure if it will be straightforward in the future, but yeah. So f, y, z equals, okay. I'm just writing the general expression or general equation that was given to us. x3y plus y cubed z plus zx cubed at point 1, -1, 2, 5. 2, 5. Why did I do a vector above that? 2, 5. Okay. So this is your x, this is your y, this is your z, and I don't know why he gave us the w, but for this equation, you don't have to worry about this 5 because we're not solving, we don't care about your w here. We only care about the x, y, and z here, all right? So here is just asking find the gradient vector at p naught. Okay, it's asking for the vector and not the general expression. Let's see how I did this. Let me go to number 6.4. All right, so 6.4. 6.4 ask find the gradient vector of the value or of the function. We know that we need to find, and just like this, 6.1, our gradient vector, now that it's with 3 variables, is gonna be the same idea, f of x, f of y, and f of z. For 6.1, all we did was f of x and f of y, but now for 6.4 with the 3 variables, now we have f of x, f of y, and f of z. So what does that mean? Like we said, your f of x, we're going to solve for your f of x, f of y, and f of z, and this is just going to be a repetitive process. So if you understand how to do it for f of x, then you will understand how to do for f of y and f of z. It's a pretty repetitive process. All right, so f of x, like we said, is equal to your partial derivative of f with respect to x, which also equal to your derivative of x of the given equation. And this given equation, I will underline it in blue for you to know which one I'm going to use, is right here. All right, so it's going to be x3y plus y3z plus xz cubed. All right, there you have it. And now we're going to take this derivative of this. So this is going to be 3x squared y, right? Plus, there's no x value here, so that becomes 0. I'm not going to write it in here. And this is just going to be plus z3. Yeah, and that's your f of x. Now let's do your f of y. Your f of y is going to be the same process. F of y is equal to your partial derivative of f with respect to y, which is just going to be your d of dy, so your derivative of y. Keep in mind, I know I said this earlier, but this is a partial derivative, and this is just a derivative. They're two different symbols. I just don't know how to draw partial derivatives, so I just did it like that. So keep in mind that these two things are different. They're not the same. Okay. Continuing, let me write this in blue now. Your x cubed y plus y cubed, oh my God, y cubed, y cubed, thank you. Yep, z plus x z cubed. Now you're going to take the derivative with respect to y, or derivative of y. So this is just going to be x cubed because there's a y value in there, and the derivative of y is just 1, plus 3y squared z plus, no, actually, no, there's no plus because there's no y value here, so it'll just be 0. So that's your x, or that's your y. So let me just clarify. This is your f of x. This is your f of y. See how simple it is? It's actually very easy. At first, when I saw this, when we released it, I was like, yo, damn, I'm about to fail this one, but no, it's pretty simple. So like I said, your f of z is equal to your partial derivative of x with respect to z, which also equals to, whoops, your derivative of z of your equation that we were solving for, which is going to be your x cubed y plus y cubed. Like I said, this is so repetitive. This is really repetitive. So if you get the gist of how I'm doing it, then I feel like you'll be solid for this exam. All right, so derivative of z. There's no z value here, so that'll be 0. There's a z value here, and the derivative of z is just 1. Okay, and then there's a z value here, so it'll be 3x z squared. Let me just make sure I got all of these things right. Yeah, I got all of these things right. All right, yeah. So now that we have our x, our f of y, f of x, our f of y, and our f of z, we're just gonna plug it back into this equation right here. They're all going back into that equation. Okay, so hopefully I'm gonna take this off in like 2 seconds. 1, 2. All right, hopefully y'all got it. All right, so let's continue from where we left off. All right. So when I plug it back into the equation, this is your general expression or your general equation for 6.4. But it's not asking for your general expression, it's asking for your general gradient vector, or your gradient vector, I'm sorry. So all I'm doing right now is just plugging what those values of f of x. Let me just write it one more time. So for those that are still confused, they will understand. So all I'm doing here is just I'm going to plug those values back in. So remember, f of x is 3x squared y cubed, well, no, just y, plus z cubed. That's for f of x. Or now our f of y is going to be x cubed plus 3y squared z. That's our f of y. And then now our f of z, which is going to be y cubed plus 3x z squared. Okay, and that's our f of z. So let me just remember f of x, f of y, and your f of z. Okay, it's pretty straightforward. And now, like I said, it's asking for your gradient vector. How we find a gradient vector is very easy. It's just basically saying plug those values that were given to us. And remember that our x, y, z values from the given equation or given question numbers from that question was 1, -1, and 2. Remember, these are from the question that was given to us. And all we're going to do is just plug it back in. So 3 times 1 squared times -1 plus 2 cubed. This is for your f of x. Remember, 3 times 1, because x is 1, x, y, z, 1 times -1 plus 2 to the third power. That's your f of x. Your f of y is just going to be 1 cubed plus 3 -1 squared times 2. And that's your f of z value, or f of y value. I'm sorry, your f of y value. Okay, now your f of z value. Your f of z value is just going to be here you go, -1 cubed plus 3 times 1 times z squared, which is going to be 2 squared. So let me color code this so this doesn't feel confusing. This is your f of x, this is your f of y, and this is your f of z. Okay, so let's rewrite this equation. So f of 1, -1, 2, which will equal, when we plug in this solving for it, so 3 times 1 squared times -1, I need some water, 2 times plus 2 to the cube, or third power. This will be 5. Okay, so your f of x is 5, comma. Now let's solve for your f of y. So your 1 cubed plus 3 times -1 squared times 2. This will be 7. Remember, I'm getting this by just plugging back in. So this is your f of x, f of x, f of y, and now let's solve for your f of z, your f of z. So -1 cubed plus 3 times 1 times 2 squared. And I'll just give you 11. And there you have it, 11. And we got this from the f of z value. All right, so there you have it. It says your vector will be 5, 7, 11. Like I said, I don't know what it's called, but if you want to do Cartesian coordinates, it'll just be 5i plus 7j plus 11k, because your x is your I, your y is your j, and your z is your k. But let me just quickly write it the way that the answer is answering. So your gradient vector, this means your gradient. Gradient vector 1, -1, 2 will equal the 5, 7, 11. And that is the answer for 6.4. Let me do it in red. So this is your answer for 6.4. Like I said, it's pretty straightforward. And then 6.5 is the same idea as how 6.3 was to 6.1. You're just finding your maximum direction value, and then you're finding the vector that correlated to that maximum direction value. Alrighty, I'm gonna clear this, and we're gonna start with 6.5. 6.5, nice, 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 nice. Oops, sorry, 6.4, no, 6.5, yeah, 6.5a. All right, so this is the last one. What is the maximum rate of change of w equals f of x, y, z at point P, point P. So pretty straightforward. We're gonna use that equation again. Remember in our last one for 6.3, it was the max direction of your gradient vector of x naught, y naught, but this time it's gonna be a z naught, which equals your absolute value of your gradient vector that we solved in 6.4, which was, here I'm just gonna say x naught, y naught. Oh, no. Your x naught and y naught are two different things. Okay, so this will be your f of x, your f of y, and your f of z. Right. Hopefully I wrote this as well for 6.3. If I didn't, just keep in mind that is actually supposed to be your whatever your f of x value and your f of y value with those vector numbers plugged into those things, right? And from that we got, I'm gonna write it again. So from that we got that our maximum direction with given this the values of -1, -1, and 2, like I said, this is the three values that were initially given to us, which was 1, -1, 2, and then that 5, which was the w, but we didn't care about it, equals the absolute value of 5, 7, 11. Okay, and by doing this, all we got to do to find the maximum value is just take the square root of 5 squared plus 7 squared plus 11 squared, right? Yeah, just making sure. 11 squared. And by doing that, we got that the maximum du f from 1, -1. I'm sorry if you can hear my clicking voice is actually very intense. All right, so the square root of 5 squared plus 7 squared plus plus 11 squared is going to give us a value of the square root of, wow, the square root of 195. And that is the answer for 6.5a. I don't know why he said 9.5a. It's 6.5a. That's the answer for 6.5a. And remember, like I said, for 6.5b, it's pretty straightforward. It's just asking where is it being maximized. And it's just the value that we solved for, which was 5, 7, and 11, because this is where we took the absolute value from. So remember, part B of both 6.5 and 6.3, you're just writing the Cartesian coordinates or whatever this thing is called into the answer. So it's just going to be 5, 7, and 11. So yeah, that was basically it. That is all of exam six, I believe. Yeah, it's not bad. It's pretty straightforward. Hopefully my work helped to make it easier for you to solve these problems, and hopefully you did good in the exam. But yeah, hopefully y'all liked it. All right, bye. That's all I got to say.